Hello and welcome to McLean 360. In this video, I want to introduce you to torsional vibration systems, and let's start with some fundamental equations. Torsional systems is coming from our strength of materials class. Let's do a review of what we did in torsion. So we said that whenever any shaft is subjected to, for instance, consider this shaft over here, is subjected to a torque, then there is a tendency of some angle of twist. Okay, so basically we are assuming that if, let's say, this is the axis of the shaft, we are assuming that there is going to be some twist. Okay, so we are assuming that there is going to be some tendency for a certain angle of twist over here. Let me draw it bigger so you get it. So what we are trying to say is that there is a tendency for this twist over here. Okay, so why is it twisting? So it is actually twisting because we have been given, or we have subjected our shaft to torque. Now, from the strength of material class, this angle of twist, let's call it phi, is given by TL over GG. All right, this is actually the angle of twist. Now, interestingly, what this is telling us is that, if I am interested in the stiffness, what is the definition of stiffness? So all the time, the force in a spring can be related as some stiffness times some deflection. Okay, always we can relate the spring force to some stiffness times the deflection. Therefore, if I am able to make the load or the force divided by the deflection, the subject, then the quantity which I get is going to be my stiffness. So if I have TL over GJ, then I expect that if I make T, which is the force or the torque or the load, divided by the angle of twist, which is form of like the deformation over here, then I expect that I am going to get what? GJ. So what am I going to get? I'm going to get GJ over L. And this GJ over L is nothing but the spring stiffness. So mostly we call this KT. So KT means the torsionally or the torsional equivalent length. The torsional equivalent stiffness. All right. So GJ over L. And what this is telling us is that this is actually coming from the shaft. All right. So what we are trying to say right now is that whenever I have a shaft and this shaft is connected to a rotor, so this is actually a rotor which is actually turning. All right, a rotor is turning like this. So in real world, the rotor is like any device which can actually turn. For instance, a flywheel. Okay, a flywheel can be turning like that. And we are saying that as this is turning, because it is connected to the shaft, our shaft will. So in fact, the shaft is trying to oppose the rotations. So let's call this rotation here, theta 1. So what we are trying to say is that as this is rotating, the shaft is trying to oppose it. And this stiffness is what we are calling what? The GJ over L, which is actually coming from the shaft material. Okay. Now let's try to understand this better from strength of materials. The J over here is what we call the polar moment of inertia. So this J is the polar moment of inertia. Polar moment of inertia. Now what happens is that if I have a system which is actually having a shaft of uniform diameter, so for a shaft of uniform diameter, J is given by pi d4 divided by 32. All right. But if I have a hollow shaft, so if I have a shaft which is such that it has got inner and outer diameter, so we call it a hollow shaft. For a hollow shaft, what happens is that the J is going to be pi over 32 d out 4 minus d in 4. So basically we are saying that if I have a hollow shaft and then it has diameters, let's say that I have d1 or di, and then I have the diameter which is what, d out. So basically the external diameter and then the outer diameter and the inner diameter, then I'm going to expect my J to be this. So the J is actually the polar moment of inertia. All right. Now, we need to also understand that the J is the shear modulus of rigidity. The shear modulus of rigidity. And this is coming from the, the bending test or the torsion test, all right? Rigidity. So if you do a torsion test of the material, you can get the J. But what do we know? So we know that shear stress, tau, is proportional to shear strain. And the constant of proportionality is the J. So we can also say that shear stress is the J and then multiplied by the gamma. In fact, we are saying that this is shear stress, okay? This one is shear stress. And then this one is the shear strain. So we are basically trying to review our strength of materials class, what we did in torsion. Now, it must be noted that this shear strain is also the same as the radius times the angle of twist divided by the length. Okay? Alright. So with these equations, you can be able to solve any question with this equation. So let's say that this is, let me call this, so starting from here, maybe this is equation, okay, so this TL over GJ is, let's say, some equation 1. And then maybe, let me call this equation 2. And then let me call this equation 3. There is another equation which says that the torque times the radius divided by the polar moment of inertia. So this is also relating the shear stress to the torque and the radius as well as the polar moment of inertia. So if you have these 4 equations, you can actually go and solve, you can solve any question on torsion, right? Enough of our strength of materials. Let's come back to vibrations. So we are just adapting what we know from strength of materials, and then we are just trying to get a torsionally equivalent stiffness. So since we now know that all the time we are going to use the GJ over L, I hope it's clear now. Okay, having known this, let's come back to our system here. So this system is actually a single rotor system. You have only one rotor here. So we call it a single rotor system. All right. Okay, so let me bring it down so that you get what I'm saying. All right, so over here, what do you see? So you see a shaft, right? You see a shaft here, and this shaft is having a diameter D. So this is actually the shaft over here. In fact, this is actually a fixed support. This is a fixed support here. And what do you see? You see that this rotor is free. So mostly we call it a fixed free system. A fixed free system, which is actually a single rotor. So I have a single rotor, and this rotor is turning. So this is what we are trying to say. If I decide to displace this rotor, if I give it some angular displacement, theta, in this sense, we expect that our shaft will give it some kind of resistance, okay? So that resistance is what we are calling KT theta. Let me try and draw the free body diagram. so that you get what I'm saying. So in effect, this is how it's going to be. So let's say that you displace your rotor through theta. We are saying that this shaft will resist it, and it will resist it by kt theta, which is actually the spring force. So we are modeling, so this is what we are saying. We are modeling our shaft as though a stiffness or a spring with stiffness k theta. All right, that's what we are saying. Don't forget that the spring force is always the stiffness times some deflection. Now, if I sum torques or if I sum moment, okay. So if I sum torque or if I sum moment, then I'm expecting that. So Newton's second law, summation of moment or torque in the direction of positive displacement. What am I going to get? So for this one, I expect that no, this one is not equal to 0. It's actually I theta dot dot. This is actually just saying that Newton's second law. So summation of forces will be mass times acceleration. All right. So basically that is what is here. Let's do that. I'm going to get minus k t theta. Why minus? Because this shaft is going to oppose the rotor, and so minus. There is no other external force, so it should be equal to I theta dot dot. Now this quantity I here is analogous to the mass. So if I have a linear system, I will be looking at the mass or the inertia actually. But if I am looking at a torsional or a rotational system, then I'll be interested in the inertia. And this inertia is actually the mass moment of inertia. Okay. So we call it the mass moment of inertia. This quantity I is what? The mass moment of inertia. And the mass moment of inertia is actually a standard. So for every given shape, we have the mass moment of inertia. And sometimes the mass moment of inertia can be given by mass times radius of gyration squared. All right. So all these, this is actually some part of a certain course, which is actually dynamics of machinery. So most of the students are familiar with this because you take a course in dynamics of machines before you do vibrations. All right. Others do it together. So I'm going to get, for now, let's take a hold on the I for now. Let's say that I theta dot dot plus k t theta is 0. This is the fundamental equation for a free fixed single rotor system, where kt is what? So this kt is what? Gj over L. Okay, this kt is Gj over L, which is nothing but the torsional stiffness of the shaft. Okay. All right. So at this juncture, let's try and find the natural frequency. So in some of the textbooks, this is how they do it. They try to draw the schematic of this system. So this is the schematic anyway. So this is the schematic. This is the shaft length. And this is I. So we want to find the natural frequency. Omega n squared is actually kt over I. Therefore, omega n will be the square root of kt over I, which is actually Gj over IL. In fact, this is actually the natural frequency of our torsional system. So this is the natural frequency of our torsional system. Pay attention to this one. It is going to follow along through all what we are going to do in torsional systems. The natural frequency of a torsional system is always Gj over IL. or Li, the same thing. So this is the natural frequency for you. Again, this is a single rotor system. All right. Okay. So let's look at a two-rotor system. If I have a two-rotor system, what will happen? All right. So before we look at a two-rotor system, let's look at when I have a single rotor attached to two shafts. Okay. So a single rotor attached to two shafts. Now watch this. If I begin to give this rotor some displacement or angular displacement theta, what will happen? This shaft will try to resist it by kt1 theta. Again, this shaft will resist it by what? kt2 theta. Now looking at it carefully, then I can say that this so these two shafts will give it like some form of um, resistance. So using the Newton's second law applied to torsional systems or angular systems, then this is what we are saying. We are going to sum all the angular displacement, or we are going to sum moment actually, and then it will be positive in the direction of displacement. So the angular displacement was actually in this direction. Actually, it was in this direction. So we are expecting that every so it should be equal to what? I theta dot dot. Now watch this carefully. What do you see? It's going to be what? Minus k1 t theta, or let's say kt. So minus kt1 theta minus kt2 theta, because these spring forces are actually going to oppose the angular displacement of the rotor, right? Then I equate this to I theta dot dot. All right. Now, again, this I is the mass moment of inertia, right? Mass moment of inertia. So mass moment of inertia. All right. So that is it for you. Now watch this. Again, I expect that I theta dot dot, so I theta dot dot plus kt1 plus what? kt2, and then theta will be equal to what? 0. In fact, this is actually the equation of motion for this system. And what happens is that, for this system, the kt1 will be J over L1, right? And then kt2 will be what? J over L2. Now, if we assume that, our shaft material is the same with different length L1 and then L2, but then the GJ is the same, then in that case, I can factorize out. So this is what I'm saying. So I'm saying that but then let's find the natural frequency so you get what I'm saying. Omega n squared is going to be what? Kt over what? Over I, isn't it? Okay. So Kt over I. Now watch this. What is it going to be? Looking at this clearly, you can say that the Kt, so if I take the square root, is going to be Gj over L1 plus Gj over what? L2. Then I multiply all of this by what? 1 over I. So what I was trying to say was that depending on whatever you have there, if you assume that the same shaft material, then you are going to get, you can factorize, J out. That's what I wanted to say. If the same shaft material, then you expect that it's going to be square root of what? J over J, J over I, J1 over L1 plus J2 over L2. All right. So in fact, that is it for you. And again, this is the natural frequency to radian per second. All right. Let me go back. The natural frequency which I did here for the single rotor system, this is also radian per second. So I have my natural frequency over here. So that is it. Actually, that is it. And so this is a single rotor system with two shafts. Okay, this is a single rotor system with two shafts. So sometimes this system is called a fixed system. A fixed system. You know, this is fixed. This is also fixed, right? So that is a fixed system. A single rotor fixed system. Let's look at two rotor systems. Okay, again, don't forget that. Again, don't forget that the J1 is going to be pi D14 over 32, and then the J2 is going to be pi D24 all over 32. So I'm talking about the J over here. You know, this shaft will have J, and this shaft will also have J, which is what? Pi D1 to the power 4 over 32, and this one will be pi D2 to the power 4 over 32, where the D is the diameters. All right. So now let's look at two rotor systems. Let's look at two rotor systems. All right, so let's look at a two rotor system. So if I say a two rotor system, I have two rotors, and these rotors are actually having each of them. So this is what we are saying. Let's say it is theta 1. Let's say this is theta 2. So basically, with a two rotor system, I have two independent coordinates, right? So this is actually a multiple degree of freedom, right? A 2 degree of freedom system. You know, each rotor can do um, theta 1, theta 2, right? Now I have a shaft connected between them. So this time around, the shaft is going to do relative, right? So this is what I'm saying. If I subject this theta 1, then there is going to be a relative, you know, k t, right? And the force here, in fact, the force here is actually depending. So this time around, it's not going to be theta, but it's going to be actually theta. So this is what I'm saying. Let me do it better. Let me first of all bring it like as though they are linear systems. I think the best way to look at it is to look at it as linear system. Let's say this is M1 connected to a spring, and let's say this is M2. Let's say this is X1 of T, and then let's say this is X2 of T. Now, interestingly, what we are saying is that, you know, this system, which is the two rotor system, behaves like this linear system. Okay. So if I want to draw the free body diagram, actually, it will be M1, and then what? So this one will be K, X1 minus X2, and this arrow will come here, M2, then I have what? X2 of T. So this is when I actually look at the, if I look at the direction of the arrow, isn't it? So I'm going to do the same thing. This is what I'm going to do. The spring force here will pose this, and then the spring force will be in the same direction with this, but the value of the spring force is going to be K T theta 1 minus theta 2. Are you okay? So this one is actually a linear system, but this is a rotational system. All right. If I do this, then I can take my time and then write the equation of motion. So let's look at the equation of motion. So equations of motion, starting with the first rotor, what can I say? So I can say that summation of torque or moment positive in the displacement. So starting with theta 1. Let's start with theta 1. or for the root 2, I1, okay? So this is the assumption. This root 2 is I1, the mass moment of inertia, and this is I2. So let's start. It's going to be what? So it's going to be equal to I, okay, so I1, theta 1, dot, dot, okay? Let me bring it down. So summation of moment is I1, theta 1, dot, dot. And then I'm assuming that the positive displacement is in the direction of the displacement. So what is it going to be? Watch this. You can see kt theta 1 minus theta 2, right? But this theta 1 minus theta 2, you can see that the arrow is in this direction. All right. So it is opposing the direction of the it's opposing the direction of the theta 1. So we are going to negate it. So it's going to be minus kt theta 1 minus theta 2. And this will be equal to what? I1, isn't it? You don't see any external force acting on, the first router, right? So I expect that I1 theta 1 dot dot plus kt theta 1 minus theta 2 is going to be what? 0, isn't it? So in fact, this is the equation of motion of the first rotor. And then if I want the second rotor, what am I going to get? Let's consider the second rotor, all right? So considering the second rotor, what am I going to get? It's going to be, again, summation of moment positive in the direction of this angular displacement will be I2 theta 2 dot dot dot, right? So looking at this one, it's going to be what? Theta 2 is coming here, right? But what do you see? You can see that the spring force will be in the same direction as what? The theta 2. But the spring force is actually kt theta 1 minus theta 2. The only difference is that if I look at theta 1, it will be opposite. But if I look at theta 2, it will be the same direction. All right. So basically we are referencing everything we are doing as analogous to the linear system over here. I hope you get it. So because you see that with the M1, the arrow was opposite to the displacement, but with the M2, the arrow was in the same direction, isn't it? So what is it going to be then? Over here, I can say that so I have K2 theta 1 minus theta 2. This time around is going to be positive. So we got what? I2 theta 2 dot dot, isn't it? So if I rearrange, I'm going to get I2 theta 2 dot dot and minus kt theta 1 plus what? Kt theta 2. But this one, it will be 1 plus what? Kt theta 1. So kt theta 1 minus kt theta 2 to be 0. And this one will be 0. So this is the equation of motion for the second rotor. So this is I2, and this is for the first rotor. Now let's try and get the two equations into a matrix form. So we are saying that so this is what we want to do. I theta dot dot plus k theta as a stiffness matrix. Then we are going to do, theta, okay, to be equal to 0. Let's do this and let's see what will happen. So you want to ask yourself, so this is going to be theta 1 dot dot, and over here I have theta 2 dot dot, okay, plus theta 1, theta 2 to be equal to what? 0. So the question is, we are going to place equation 1 and then equation 2 in a matrix form, all right? So what is the coefficient of theta dot 1 in equation 1? That is I1. So this is what we are saying. But in equation 1, the coefficient of theta 2 dot dot is what? 0. There is no theta 2 dot dot in equation 1. All right. Don't forget that. So this is what we are doing. The row represents the equation and the column represents the unknown. All right. So the first row will correspond to equation 1. What is the coefficient of theta 1 in equation 1? Kt. What is the coefficient of theta 2 in equation 1? So that is minus kt to be 0. Okay. Then again, what is the coefficient of theta 1 dot dot in equation 1? Do you see, sorry, in equation 2, the second row is equation 2. Do you see theta 1 dot dot here? No. So this is going to be 0. But the coefficient of theta 2 dot dot is what? I2. All right. Now, then you come to this side. What is the coefficient of theta 1 here in equation 2? That is this one. Minus kt, right? And the coefficient of theta 2 in equation 2, that is kt. All right. So this is what we are going to do. Let's assume that there is a parameter called lambda, which is actually equal to omega n squared. All right. Let's assume that this parameter is lambda, which is omega n squared. And then we are going to also assume that theta dot dot will be minus k minus lambda theta. Okay, let's do this. We are saying that theta dot dot is minus lambda theta, and then lambda is omega n squared. Okay, let's do that and let's see what will happen. So I1 0 0, I2, then minus lambda theta 1 minus lambda theta 2. If I do that, plus to kt minus kt minus kt, and then kt, and then theta 1 theta 2 to be equal to 0 0. All right. If I do this, so I can rewrite this first matrix as what? Minus I1 lambda 0 0 minus I2 lambda, right? While I still have theta 1 and then theta 2. Again, plus, so plus, this side is going to be what? Kt minus kt minus kt and kt, and what is it? So it's going to be theta 1, theta 2, 0 0. All right. Now at this juncture, since I have theta 1 2 theta 1 2, then I can add, isn't it? So if I add, it's going to be kt minus I1 lambda. This will be 0. Sorry. So I'm adding the matrix, all right? So I'll add this one to this, and then 0 plus minus kt is minus kt. Again, 0 plus minus kt is minus kt. And then if I add minus I2 lambda to kt, it's going to be kt minus I2 lambda. Theta 1, theta 2 should be what? 0. Now, what I've gotten right here is an eigenvalue, eigenvector problem. So an eigenvalue or an eigenvector problem. So how can I find theta 1 and theta 2. So this is what we are saying. We are going to assume that, in other words, this is what we are saying. We are multiplying a matrix and a vector. Then we are getting 0, isn't it? So two things. Either the matrix is 0 or the vector is 0. Or both of them are 0. So three things, isn't it? Now watch this. You see, if I say that the matrix, if I say that the vector, so if I say that this theta 1, theta 2 is 0, then we are not doing vibration. We need to stop making this video and we need to stop doing the course. Because the theta 1, the theta 2 represents the amplitude of angular displacement. Okay? But, in fact, if this is not 0, then our matrix is 0. But we cannot say a matrix is 0. But rather we say that the determinant of the matrix is rather what? 0. So we are going to set the determinant of this matrix to 0. In other words, we are going to say that, so in other words, we are saying that, you know, our KT is actually, so this is what we are saying. The determinant of KT, I lambda minus KT minus KT, and then KT minus I2 lambda is what? 0. Okay. So over here, we are going to solve for lambda. Okay, we are going to solve for lambda. The determinant of this matrix is going to be KT minus I1 lambda multiplied by KT minus I2 lambda minus KT squared, isn't it? At the end of the day, minus minus will be plus. Okay, to be what? 0. Now, it is interesting to know that the KT is nothing but GG over what? Over L. The GG over L is the KT. Are you okay? Because that is actually the shaft material, the stiffness. So this is what we are saying. Our KT that we are talking about, this one, is actually the stiffness, all right? So this is what we are going to get. We are actually going to get, okay, let me do it. Let's try and, you know, solve this one. I'm actually going to get GJ over L, which is actually KT, I lambda, right? GJ on L minus I2 lambda. GJ over L squared. Okay. So I will multiply GJ over L and I'll get GJ over L squared over here. Then I will come and take GJ over L with what? I1 lambda, right? So I'm done with the first part. Then I will come and take again. So I'm multiplying GJ over L by what? GJ over L, you get a squared. Again, GJ over L by, it's going to be I2. So I'll now use minus I1 lambda GJ over L, right? And then I'll do what? Minus I2 lambda. Okay, so it's going to be plus. Okay, let me take my time. So if I do this, that is the first part, then plus I1, I2 lambda squared. Is that right? Okay. Minus GJ over L squared will be 0. Interesting. So what are we trying to say? GJ over L squared will cancel GJ over L squared. And then what are we going to get? So we have I1, I2 lambda squared minus. So in terms of lambda, this is going to be Gj over L into what? So I can say I1 plus I2 lambda to be what? 0. Is that not it? Alright. So in fact, this is a quadratic equation in Gj over L. Now to get the root of this equation, what are we going to do? Alright, so looking at the almighty formula, we can say that lambda is what? Minus what is the almighty formula anyway? AS squared plus BS plus C equals 0. The almighty formula is saying that X is minus B plus or minus the square root of C squared minus 4AC divided by 2A, right? So we are just going to apply what we have been doing since our elementary school. So lambda is going to be minus B. So when we say minus B, that is the coefficient of X. So over here, minus B is actually the coefficient of lambda. It is already negated. So I will make it positive by saying Gj over L, I1 plus I2. All right. And then, okay. So lambda. So that is the coefficient of it. Then plus or minus C squared. So now, interestingly, we don't have C squared, isn't it? I'm sorry, B squared, sorry, it's actually B squared minus 4AC. B squared minus 4AC. So B squared is, again, this is the B, right? This is the B. Okay, let me bring it down. So in fact, lambda is nothing but Gj over L, I1 plus I2, that is the B, the coefficient of lambda, plus or minus, again, the square root of B squared, that is the B, so Gj over L, anyway, minus Gj over L, I1 plus I2 squared. Is that not it? And then I will do what? Minus 4AC. Now watch this. There is no constant term. So the 4AC part will be 0, isn't it? There is no constant term. So that will be 0. And I will divide everything here by what? 2 times A, which is what? I1, I2. Alright? If I do this, then what am I going to expect? So I'm expecting that I will get lambda to be what? So lambda is Gj over L, I1 plus I2. Then I'll divide this by what? 2I1, I2 plus or minus square root of. So but then what is this? The square root of this squared. So it means it will even cancel it. Then minus Gj over L multiplying what? I1 plus I2. So the root will cancel the square. Then I will divide this by what? 2I1, I2. Is that right? Finally, what is it going to be? Alright, so at this juncture, let's take our time and do it. This is interesting. So to get lambda 1, I'll make it plus. So Gj over L, I1 plus I2, all divided by 2I1 multiplied by I2, plus. Again, so I'm going to make this one plus. So I'm expecting minus Gj. Of course, there is a minus sign here. So if I have plus, I expect that this will be minus, right? So Gj over L, I1 plus I2, all divided by 2I1, I2. Ooh, do you see what I'm seeing? You see that the whole thing here is the same. What are you suspecting? We are suspecting that the whole of this is the same, therefore it is 0. Wow. In fact, this is very interesting. If you don't know, this is actually very interesting to know that, what did we say? We said that lambda should be omega n squared, which is actually the natural frequency. But it looks like what we have is like one of the natural frequency is 0. This is interesting. And then to get the other natural frequency, we are going to make it a plus. We are going to make it minus, all right? So it's going to be Gj over L I1 plus I2 divided by 2I1 I2 and then minus, but this time if I make it minus, there is already minus sign, so it's going to be plus. You get my point? There is already a minus sign there, isn't it? There's already a minus sign there. So once I do that, so there's already a minus sign here. So if I make it minus minus, it's going to be plus. So Gj over L I1 plus I2 all divided by what? 2I1 I2. This is like the same thing. So it's like you can take one of them and multiply by 2, isn't it? Gj over L I1 plus I2 multiply by what? 2I1 I2. Is that not it? Now, interestingly, what happens is that for this one, what do you expect? So what are you going to expect? Ooh. Can you help us, anyone? So let me take my time and simplify this. 2 times Gj over L I1 plus I2 and then what else? Okay, so this is actually dividing. So this is what we are saying. This is actually dividing 2 I1 I2, isn't it? So what will happen? So it means that lambda 2 is nothing but 2 Gj over L I1 plus I1 multiplied by I2. Then I multiply it by what? 1 over 2 I1 I2. Wow. This is very interesting. So what is lambda 2 then? In fact, lambda 2 is nothing but oh no, my bad. I didn't bring. No, let me take my time. Let me go back and do this well. Lambda 2 is actually going to be 2 times Gj over L I1 plus I2. Then I'll multiply it by 1 over 2 I1 I2. So this 2 will cancel this 2. Then I'm going to get Gj. Then I'm going to get Gj over L I1 plus I2 and then divided by what? I1 multiplied by I2. And in fact, this is actually omega n squared. So this is the second natural frequency, which is going to be the square root of Gj over L I1 plus I2 all divided by I1 I2. This is interesting. So in fact, what we are saying is that, so this is what we are saying. In summary, whenever I have a two-rotor system, it will have two frequencies, all right? But one of the frequencies is 0. So we need to find the other frequency. That's all what we are saying. That's all what we are saying. If I have a two-rotor system, one of the frequency is what? Is 0. I need to find the other frequency. And that frequency will be given by, root of what? Gj over L, I1 plus I2 divided by what? I1 multiplied by I2. But mostly what we normally do is Instead of doing the whole of this, we don't do this approach. But if you do this, it's also accepted. Mostly we use what we call the nodal analysis. The nodal analysis. Okay. So let's look at the nodal analysis, and then I will end this video for part 1 of the torsional systems. So what is the nodal analysis anyway? Alright, so let's look at the nodal analysis. Sometimes you don't use the actual approach, the first approach we did. Sometimes what you normally do is that you are going to use the nodal analysis. So what is the nodal analysis anyway? We are assuming that whenever I have a two-rotor system, theta 1, theta 2, then we are assuming that there is some point somewhere along the shaft where the amplitude of vibration is minimal. So let's call this point K. So we are calling the point K what we call the node. And we are saying that at the node, what are we saying? At the node, the amplitude of vibration is 0. So in other words, if I draw the schematic, this is what we are going to get. Okay, so that is our schematic there. And what do you observe? We can treat this as a free, so in fact, this is a free system. But we can take this, we can take a section here, then we will treat this as though a free fix, okay? So it's like I've taken a section here. This is a free fixed system, and this is also a free fixed system. Can you see that? Now the assumption is that the node is a point somewhere over here, and then the assumption is that if I cut this into 2, don't forget that the whole of this is the length, okay? The whole of this is the length. So if I cut this into 2, I expect that A plus B to be equal to the length. So this is the fundamental equation, right? But two unknowns with one equation. I need an extra equation, and that equation will come from the fact that because I have two, this is actually a single shaft that was rotating. So the natural frequency of the shaft is going to be constant, isn't it? Whether I am looking at it from this end or looking at it from this end, the natural frequency of the shaft must be what? Equal to constant, right? If I do that, it's going to be, but what is the natural frequency anyway? The natural frequency of this two-rotor system, we said, is actually Gj over IL, isn't it? So for this system, omega NA will be what? Root of Gj of A divided by what? I A multiplied by A. Don't forget that now A is this length, okay? A is this length. Is that right? Okay. And the IA is the mass moment of inertia of this rotor. And again, omega N B what? Root of what? Gj B over IB times B, isn't it? But since the frequencies are the same, then omega NA should be the same as omega NB. But what am I to expect? Now what happens is that, so I can say that GJB over IB times B is the same as what? GJA over what? IA multiplied by A. Now, since the shaft material is the same material, we expect that these components are also the same. So, in other words, IB multiplied by B should be equal to IA multiplied by A. And this equation is actually the second equation. So, these two equations, IA. These two equations are necessary and sufficient. Okay, so the first equation was this one. A plus B is equal to the length, the total length, and then IA multiplied by B, IB multiplied by B should be equal to IA multiplied by A. Now it is interesting to note that the B and the A, so someone will ask, what is the node? So we are saying that the node is a point K somewhere here. But if I am able to get B, if I am able to get A, then it means that the node, so let's say that if the node is somewhere here, after solving for A, you are saying that the node is at a distance A from the rotor A. And then if you solve for B, then you are saying that our node is at a distance B from the rotor B. All right. So that is actually the 2 degree of freedom or two rotor systems. Thank you very much for watching.